Hello all. This will be my last instructional video for the week and the second to last thing that I post for this week of October 12th. And the last thing we're going to learn about in the world of limits and continuity is the squeeze theorem. After this, we will start moving on to derivatives, which is our second big topic in calculus. But let's not get ahead of ourselves. First, we're going to talk about the squeeze theorem. So this is really just a short little theorem. It's so last section we learned about the intermediate value theorem, and this one is called the squeeze theorem. These are two of the big theorems that you'll learn in calculus. And here's the basic idea. If two functions are squeezed together at a particular point, then any function trapped between them will get squeezed to that same point. So this is dealing with limits. And I have an image below that you maybe see if you printed these out. And like I just said, the squeeze theorem deals with limit values rather than the function values because we know the limit can exist even if the function is undefined at that point. So this is dealing with the limits themselves rather than the actual function values at that point. And sometimes you'll hear this said as a sandwich theorem or the pinch theorem. Okay, so what this really means is here's all the math symbols. If we have a function h of x, which is less than f of x, which is less than g of x, for all x in an open interval containing c, and if the limit of h of x and the limit of g of x equal the same thing, that means the limit of f of x exists and is also equal to L. Okay, so that was a lot of math and math language. So take a look at this picture. This is a middle function, so maybe I'll just write on this and kind of help you see what's going on here. So we're going to say this middle function, this red line right here, is f of x. If we have a function f of x, we're trying to find the limit of f of x at some value a. I used c up here, but this image is for a. Then we can find functions. Let's see, g of x up here and h of x down here, such that f of x is always in between g of x and h of x for this interval. And, all right, and here's the key. If the limit of g of x as x approaches some value a on this graph, I use the value c up here, is equal to the limit of h of x as x approaches some value a, if those two limits are the same, that means the limit of the equation in between them also has to be the same. It has to be the same limit, these two. So you see they kind of squeeze the middle function, so then we can find the limit. And then I have this nice little graphic here. F of x is being squeezed by g of x and h of x. So we're just squeezing two functions. And if the function above our function and the function below our function approach the same limit, that means our f of x has to approach that limit as well at that point. We'll kind of talk about some examples. So I've got 4 examples for you. And here's the first one. Using the squeeze theorem, show that the limit as t approaches 0 of t squared times sine of 1 over t is equal to 0. Okay. First, I'm going to go to Desmos. I'm going to move this over here and get rid of these. And I'm just going to graph sine of 1 over x. So you can kind of see what this really looks like here. Actually, I'll graph a sine squared. Nope. I'm going to graph x squared times sine of 1 over x. And we're trying to prove that the limit as t approaches 0 is 0. So we know what the limit is. We just need to prove it using the squeeze theorem. So if I zoom in here, you can see that this function does approach 0 as x approaches 0 or as t approaches 0. So to find two functions that one is above this function and one is below this function, we're just going to take a look at this sine of 1 over x first. Okay, and that looks like this. So y'all, take a look at this function here. Do you see that the line 1 Okay, I need to type y equals 1. And y equals -1 are upper bounds and upper bounds for this entire function. Okay, we're going to start there for the squeeze theorem. So we can say that -1 is less than or equal to sine of 1 over t, which is also less than or equal to 1. So that means our sine of 1 over t, what we just graphed, is between -1 and 1. Okay, so that's where we're going to start here. Now, we're trying to prove that t squared times sine of 1 over t, the limit of this value is 0. So, do you see right now how this is like my g of x, this is the h of x, and then this is our f of x. So I have two functions defined where our sine of 1 over t is between them, but that's not equal to what's inside here. So what we're going to do is multiply every term in this inequality statement by t squared. So I'm going to say multiply by t squared. So if I multiply each term by t squared, maybe I can make this terms purple. So this will be a negative t squared is less than or equal to t squared times sine of 1 over t. Cool, that's the function that we need, which is less than 1 times t squared, which is a positive t squared. So I just multiplied each of these three expressions by t squared. Oh, except I didn't do this one. All right, now I did. Now I multiplied each of these three terms by t squared. And now, since the squeeze theorem deals with limits, let's find the limit of negative t squared and the limit of t squared. And if these limits are equal, and they equal 0, therefore, by the squeeze theorem, the limit of t squared of t squared times sine of 1 over t as t approaches 0 will also be 0. So let me write all that out. So the limit as x approaches 0 of negative t squared equals, well, I just plug in 0 for t. Oh, why did I write x? It should be t equals 0 as t approaches 0. The limit as t approaches 0 of negative t squared, well, that's just negative 0 squared, which is just 0. So that one's 0. Now how about the limit as t approaches 0 of t squared? Plug in 0 for t. This limit is also 0. So these are both 0. Therefore, by the squeeze theorem, the limit as t approaches 0 of t squared times sine of 1 over t also equals 0, because we found that t squared is less than t squared times sine of 1 over t is less than t squared, and if the limit of negative t squared is 0 and the limit of t squared is 0, therefore the limit of the function in between them also has to be 0. And that is the squeeze theorem. All right, so let's just keep on going. I'm going to have you try this one on your own, and this will be your whole homework for the squeeze theorem. So this will be your homework, and I'll have you submit this on Canvas. Submit the work on Canvas. So this one will be solved very similarly to what we did up here. So I'm going to go ahead and skip this one. This will be your only problem for the homework on the squeeze theorem, and then we'll walk through the next two examples together. So Let's suppose there are three functions such that f of x is less than or equal to g of x is less than or equal to h of x when x is near 2. Suppose further that f of x is negative 1/3 x cubed plus x squared minus 7/3. And h of x is cosine of pi over 2 times x, where x is in radians. Let's find the limit as x approaches 2 of g of x. So we are going to use the squeeze theorem here, since g of x is in between f of x and h of x. So let's find the limit of f of x as x approaches 2. Well, we can just plug in 2. This is just a parabola, so we actually will get a value here. So this is really just negative 1/3 times 2 cubed plus 2 squared minus 7/3. And this is equal to, let's see, 2 cubed is 8, so this will be negative 8/3 plus 4. 4 is really 12/3, right? Just getting everything to be a common denominator so that it's easy to actually calculate this value. Okay, let me double check. Negative 8/3 plus 4, which is 12/3 minus 7/3. And all of this is equal to, let's see, negative 8 plus 12, that's 4 minus 7. So we get negative 3 over 3. Oh, that's just a negative 1. All right, so that's the limit of our f of x. What's the limit of our h of x as x approaches 2? Keep in mind, if the limit of h of x as x approaches 2 is negative 1, then by the squeeze theorem, the limit of g of x is also going to be negative 1. But if the limit of h of x as x approaches 2 is not negative 1, then we can't use these two functions to find the limit of g of x. This squeeze theorem only works if these two limits are the same. And that word is same. Okay, so let's find the limit of h of x as x approaches 2. So h of x is cosine of pi over 2x. So let's just plug in 2 and see if we get an actual value here. So cosine of pi over 2 times x, which is 2. This is really just the cosine of pi over 2 times 2 is just the cosine of pi. And if you take a look at your unit circle, or I suppose you can use a calculator. Let's see, cosine of pi, that will be negative 1. All right, and our limits are the same. Therefore, by the squeeze theorem, the limit as x approaches 2 of g of x equals negative 1. I'll zoom out a little bit. Equals negative 1 as well, since g of x is in between f of x and h of x. All right, and let's take a look at this last example. So we want to find the limit of x over sine of x as x approaches 0. Looking at the graph of this function, we can estimate that the limit is equal to 1. So I'll just graph it for you. This is going to be x over sine of x. Limit as x approaches 0 does approach 1, even though it is undefined at that point, because sine of 0 is 0. So we can estimate that the limit is equal to 1, but we should prove it using algebra, and we can use the squeeze theorem. So this is just is this student right or wrong? So one student suggests that we use the functions g of x equals negative x squared plus 0.5 and h of x equals x squared plus 1.5 in order to apply the squeeze theorem. Does this method work? Is this going to work if we use the squeeze theorem? Just take a second and think about it. And the answer is, because I'll tell you, The answer is no. Because the limit of g of x as x approaches 0 does not equal the limit of h of x as x approaches 0. Remember that the squeeze theorem really only works if the limit of your outside functions equal the same thing, and squeeze to be the limit of the function in between. So the function of the limit of g as x approaches 0 is like a half. No, it is a half. And then the limit as x approaches 0 of h of x is 1.5. These are not the same. Therefore, we cannot apply the squeeze theorem to determine that the limit as x approaches 0 of x over sine of x equals 1. So these are not functions that we can use. And y'all, that's it for these notes. That's it for this video. So this example 1 is the one task that you need to do for the squeeze theorem. And if you need any help with that, just let me know. So please let me know if you have any other questions about squeeze theorem or anything else. Please just come to my office hours if you need any help or want to talk to me directly. Yeah, and I hope you have a good week and a good weekend if you watch this on Friday.